In Chapter 12, we finally get to use our BC knowledge and apply it to MVC. We started by graphing multivariable functions, and we basically graphed two types. So one of the types that we graphed was f of xy equal to z. This graphed a surface. And then if we set z equal to a constant, f of xy equals k, this graphed a level curve. We also looked at three variable functions. So f of x, y, z equals w, for example. This would graph a solid. And then if we just graphed a specific value of w, f, x, y, z equal to k, this graphed what was called a level surface. Limits and continuity basically approach the same way we did last year, except we cannot use L'Hopital's anymore because our definition of derivative has changed. However, we could use the idea of polar to help evaluate our limits. This was especially useful if x and y were approaching 0, 0, because we could reinterpret that as r approaching 0. Differentiability and partial derivatives. Partial derivatives are basically where one of the variables is kept fixed. So for example, f sub x, you take the limit as delta x approaches 0, and you hold y constant. So we're only looking at the change in x, x plus delta x, comma y, minus f of xy, all over delta x. Differentials, we had two types of differentials. So delta z is the actual change in z of the function. So this is defined f of x plus delta x, y plus delta y, minus f of xy. But dz is the linear approximation for the change in the function. So what we use is a linear approximation in the x direction, which would be f sub x at some point, x sub 0, y sub 0, times the change in x, plus the linear approximation in the y direction, f sub y, x0, y0, plus the change in y. Now, since we are typically given the exact value for the change in x, this you might see interchangeably with dx, and this with dy, but dz and delta z are definitely different from each other as a result. Last thing we talked about was in the idea of implicit differentiation. So with implicit differentiation, we could take our BC rule of dy over dx and write it as the partial of f with respect to x over the partial of f with respect to y. But we could also apply it to our multivariable functions. For example, dz over dy would equal the opposite of the partial with respect to y all over the partial with respect to z. And the only stipulation on being able to use this one was you had to make sure that your function, whatever it was, f of x, y, z, was equal to a constant before you could start using these two formulas for implicit differentiation. We're going to start with our graphing. So starting with the first one here, I'm going to graph a set of level curves. Again, you can see that it's going to be level curves because if you set this equal to z, you would graph a surface. And then if I change z to a constant, that's going to graph just values in terms of x's and y's. So that's going to be my level curves. So I'm going to set this x minus y over x plus y equal to k. And I'm going to start solving for y. So x minus y equals kx plus ky. Let's see, so that would be y plus ky equals x minus kx. Solving for y, I'm going to get x times the quantity 1 minus k all over 1 plus k. So basically, for different values of k, this is going to generate lines with different slope. For example, if k equals 1, then y is going to equal 0. So then graphically, what I want to do is, we don't want this thing here, and we don't want this thing here. So graphically, what we want to do is basically graph a line y equals 0, and say that is when k equals 1. Now, if k equals 2, we're going to graph the line y equals x times negative 1 over 2. So we're going to graph the line y equals negative 1 half x. And so if I graph the line y equals negative 1 half x, it's going to look like this. And label that as k equals 2. And then we can go in the other direction as well. So for example, if k equals negative 1, or let's do k equals 0. If k equals 0, I'm going to graph the line y equals x. So that would be this line here. And this is when k equals 0. So basically, for different values of k, what's going to happen is I'm going to have these spiraling lines, and they're going to increase as k, or they're going to spiral in an upward direction as k increases in values. And graphically, we're going to generate something like this as a result. So that's my level surfaces, or my level curves. Now for my level surfaces. So my level surfaces, this one, for each value, I'm actually going to generate a surface. So I do need, for this one, my other axis. Alright, so again, I'm going to set this equal to k. So I'm going to have x squared plus 2y squared minus z equals k. And notice this time, if I solve the equation, or I rewrite the equation, I'll have z plus k equals x squared plus 2y squared. So if you recall from chapter 10, which is what you're going to need to do, is this generates a paraboloid. And so now I want to look at different values of k. So for example, if k equals 0, I get z equals x squared plus y squared. So this is just going to be my paraboloid center at 0. So this will be when k equals 0. If I let k equal 1, then I get z equals x squared plus 2y squared. Oh, there should have been a 2 here, sorry. X squared plus 2y squared minus 1. So this will be my paraboloid, but shifted 1 unit down. So if I draw my paraboloid, shifted 1 unit down, something like this. So that would be when k equals 1. And let's say I have k equal a negative number, like k equals negative 3. So that would be z equals x squared plus 2y squared plus 3. And that would be a paraboloid shifted up 3 units. So then the paraboloid would look like this. And you would want to label it k equals 3 as a result. Now, the different types of discontinuity. So, first thing you want to do, kind of like back in BC, is actually just factor this out. So if I factor this out, I get 2x minus 3y squared in the numerator. And obviously the first thing you want to try is 2x minus 3y squared in the denominator to see if you have a removable discontinuity. And then that leaves me x plus 4y squared as my leftover factor, and x squared plus y squared. So we have 3 discontinuities here. I can cancel out the 2x minus 3y squared, which basically means that it's removable. So I have this removable discontinuity along 2x equals 3y squared. And you can kind of see from the graph how I have this gap there. Now I also have the x plus 4y squared. So that is an asymptote along the parabola x equals negative 4y squared. And also you can kind of see that from the graph. And then the last one here would be an asymptote. And this would just be a single asymptote at x equals y equals 0. So this one here is like a planar asymptote, because an entire plane or a curved plane gets canceled out. This one here, you can almost think of as a line asymptote, because it's only at x equals y equals 0, and that's kind of where we get that spike effect when we have as x and y approach 0. Okay. Epsilon delta limits. So I want to try to explain this graphically. do the definition for epsilon delta limits, and then actually do a proof for it. So epsilon delta is this idea. If you recall from BC, basically what we would have is a function, except this time we're in 3 dimensions. And let's say we claim this is our limit right there. So the idea of epsilon delta is no matter how close I get to this limit, so this would be like L plus epsilon and L minus epsilon, it has to correspond to a value on the xy plane. But here's the difference. So because it's on the xy plane, I'm not just approaching that point from the left or the right anymore. What I have is I have this whole radius, or basically I can approach it from an infinite number of directions. So delta becomes not just a left and right measurement, but an entire radius as I get closer and closer to that point right there. So if I write this specific to the example, it's going to look like this. For any epsilon greater than 0, so for any distance around y equals, or z equals 1, there exists a delta greater than 0. So there exists a radius around x, whatever x and y are approaching, such that f of x, so in this case 2y plus x minus the limit, which is 1, is less than epsilon. So that distance between the function and z equals 1 is less than epsilon whenever. Now, for distance, because I can't use absolute values, I have to use my distance formula in 2 dimensions, which would be the square root of x minus 1 squared plus y minus 0 squared is less than delta. So the idea here is, again, I have a radius around 1, 0, and as long as I stay within that radius, then my limit, my z values have to stay within so many units of 1, which is what my function is approaching. Now I actually want to do a proof with this, so you see how it works. This one's more complicated than what you would be expected to do on the quiz or the test, but definitely want to show you how this works. So if I start from this point here. So the idea is I want to be within 1 unit, or epsilon units of 1. So I'm going to start from 2y plus x has to be within epsilon units of 1. So 1 plus epsilon, 1 minus epsilon. Now, I can't solve for a single variable, so what I'm actually going to do is solve for y in terms of x. So that's going to become y is less than 1 plus epsilon minus x over 2. And 1 minus epsilon minus x over 2. So what I can actually do with this is say, okay, y has to be bounded then between 2 lines. Negative 1/2 x plus 1 plus epsilon over 2, and negative 1/2 x plus 1 minus epsilon over 2. So I'm going to go ahead and graph this. So here, let's say we're going to graph this. So 1 plus epsilon over 2, let's say this is 1. Okay, 1 plus epsilon over 2, let's make it right there. And then a slope of negative 1/2. So here's my upper bound for y. And then we'll say this is 1 minus epsilon over 2, and my slope here is negative 1/2 as well. So my y is stuck between these 2 points. Now, I'm approaching the point 1, 0. So 1, 0 is about here. And basically, what I have to do is I have to find a circle about 1, 0 that stays within the restrictions of y being between these 2 dotted lines. So now my job is to find this circle here and find the maximum radius of that circle. Now, what I'm not sure of, which I've got to work on then, is which one that circle is actually closer to as I work it out. So basically, I need a distance between that point there, 1, 0, and one of the two lines. Now it looks like it's closer to this line here, which is negative 1 y equals negative 1/2 x plus 1 minus epsilon over 2. So I'm going to go ahead and set up my formula using that one, and then I'll show what the other one is, and we'll compare the two to each other. So here's the bottom line. I have this line. Y equals negative 1/2 x plus 1 minus epsilon over 2. I have some point here, which is at 1, 0, because x is approaching 1 and y is approaching 0. And I need the distance to this line, which means we would have to go back to chapter 10 and use the point-to-line distance formula to work this out. So the point-to-line distance formula was v cross L, magnitude of that, all over L. Alright, so first I need MV. V, if you recall, was a vector from a point on the line to 1, 0. So let's use the y-intercept for that line. So that point would be 0, 1 minus epsilon over 2. So V would equal the difference between these two, which would be 1. And let's see, negative 1/2 plus epsilon over 2. L would be the direction of the line, but that's generated by the slope. So if the slope is down 1 over 2, this is negative 1 over 2, then my vector for that would be 2, negative 1. So now I need the cross product between these. So V cross L would be, let's add a 0 to this, 0, 0. So V cross L would be 0, 0, and then it's going to be negative 1 minus 2 times negative 1/2 plus epsilon over 2. All over, and then that would be my V cross L part. So I take the magnitude of that over L, which would be the square root of 5. Okay, so let's keep simplifying. So this would become the magnitude of 0, 0, negative 1 plus 1 minus epsilon, all over root 5. So the magnitude of the numerator would be epsilon over root 5. And it turns out actually the other one is the same. So that means if I let delta equal epsilon over root 5, then I've completed my proof, because for any epsilon greater than 0, I can define a delta so that the distance requirements are satisfied. So basically what that means is my drawing here is really bad, because 1, 0 is probably closer to being in the middle, so that it's equidistant as a result. Alright, let's evaluate a limit. So I have here, the limit as xy approaches 0, 0 of 3x squared plus x over x squared plus 2y squared. So I want to show this two ways. Basically, you can prove that a limit does not exist if you can find two approaches to what x and y are approaching, and you get two different values as a result. So for example, this one, if I go along y equals x, because if I use the line y equals x, then it is going to approach 0, 0. Then my limit as xy approaches 0, 0 becomes 3x squared over x squared plus 2x squared. And that equals 1. Okay. Now, if I go along, let's say y equals negative x, I would take the limit as x, y approach 0, 0. I would get 3x squared over x squared plus 2y squared. And again, that equals 1. But that does not mean the limit is equal to 1, because technically I've only used 2 out of an infinite number of paths approaching 0, 0. For example, if I use along y equals 2x, I get the limit as xy approaches 0, 0. And this time I'm going to get 3x squared over, I forgot x squared, x squared plus, let's say, 2 times 4x squared, because y squared would be 4x squared. So this becomes 3 over 9, which is 1/3. So notice, since I can approach it in an infinite number of ways, you can't just stop at 2 or 3 or 4 and say, well, I got the same value, so therefore the limit has to be that value. So this one, we show that we get 2 different values, and therefore the limit does not exist. Now, since this one is also as xy approaches 0, 0, I can also convert this to polar. So in terms of polar, it becomes the limit as r approaches 0 of 3r squared cosine squared theta all over r squared cosine squared theta plus 2r squared sine squared theta. But notice all the r squareds cancel out, and we're left with 3 cosine squared theta all over cosine squared theta plus 2 sine squared theta, which changes with every possible value of theta, and so this is another way to show that the limit does not exist. Alright, so now to prove differentiability proof. So the idea of a differentiability proof is you want to show that delta z, the actual change of z, is mostly determined by the partials with respect to x and the partial with respect to y. And anything else left over goes to 0 as delta x and delta y approaches 0. So formally, we're looking at this. We're trying to show that delta z equals f sub x delta x plus f sub y delta y. Those are our predominant terms. But we have anything extra, epsilon delta x, and then any extra times delta y. And as long as we can show that epsilon 1 and epsilon 2 approach 0 as delta x and delta y approach 0, then we've proved that it's differentiable. So I'm going to go ahead and do that with this example. So in this example, delta z would equal f of x plus delta x, if you recall from my first slide, y plus delta y, minus f of xy. And so if I substitute this into the function, I get x plus delta x squared, y plus delta y, minus my function, x squared y minus 3xy. If I multiply this out, I'm going to get x squared plus 2x delta x plus delta x squared, y plus delta y, minus x squared y plus 3x. And one more distribution. So I get x squared y plus x squared delta y plus 2xy delta x plus 2x delta x delta y plus delta x squared y plus delta x squared delta y minus x squared y plus 3xy. Now, if you do all the math correctly, your non-delta x terms should cancel out because notice up in the beginning, everything has either a delta x or a delta y on it. So, my x squared y's cancel out, my 3xy's, oops, I have a 3xy somewhere. No, what'd I do? Oh, I never used it over here. Okay, so, I should have had here, sorry, a minus 3 x plus delta x, y plus delta y. So likewise here, if I add that, I should have a minus 3xy minus 3x delta y minus 3 delta xy and minus 3 delta x delta y. I'm sorry. Okay, so I have some extra terms here. Plus 3xy minus 3x delta y minus 3 delta xy minus 3 delta x delta y. Alright, let's try again. So then the x squared y's cancel out. There's my 3xy's, they cancel out also, because this would be a minus. So this should be a minus. And then let's see, the other should be fine. I think I just miscopied the minus. Alright, so now I want to look for my partial with respect to x terms and my partial with respect to y terms. So my partial with respect to x term would be the 2xy minus 3y. My partial with respect to y, going all the way back to the beginning, would be x squared minus 3x. So now I got to look for both of these terms in my problem here. I will get to these. Alright, so let's start with my partial with respect to x. So I need a 2xy minus 3y, both of them being multiplied by delta x. So if you notice here is my 2xy delta x, and then I should have a minus 3y delta x, which is right there. So I have 2xy minus 3y all being multiplied by delta x. Now similarly, I should see my fy terms as well. So that would be x squared times delta y, which is right here, and minus 3x times delta y, which is right there. So I also have a plus x squared minus 3x delta y. Okay. Now, all the rest of the terms are going to be either being multiplied by delta x or delta y, and I just got to pick which ones I want to use to be multiplied by delta x and which ones I want to pick to be multiplied by a delta y. So I'm going to do this one at a time. Since this one is a delta x term and this one is a delta x term, I want to put those together. So plus 2x delta y plus y delta x. Both of those are being multiplied by delta x, so I factored it out. And then I also need my delta y term, so I'll call this one delta y and this one delta y. So plus delta x squared minus 3 delta x, and both of those are being multiplied by delta y. So I will let epsilon 1 equal 2x delta y plus y delta x. I will let epsilon 2 equal delta x squared minus 3 delta x. And I hope I picked up every term that I can see. And I will say epsilon 1 and epsilon 2 approach 0 as delta x and delta y approach 0, which they do because they each have either delta x or a delta y term in them, and therefore my proof is done. So, therefore, f is differentiable for all xy. Alright, we're going to look at two other problems here involving derivatives. So the first one I want to look at is suppose that g is differentiable, capital G is differentiable, and g of xy is equal to this. I want to basically show this relationship has to be true. And this is where I want to basically demonstrate chain rule. So let's start with the partial of lowercase g with respect to x. So that's basically the partial of uppercase g with respect to x. But notice I have a composition of functions because u and v are my variables for capital G, and u is a function of x and y, and v is a function of y and x. So u equals x over y, and v equals y over x. So that means if I want the partial with respect to x, and they're both in u and v, I'm going to have to do the partial of g with respect to u times the partial of u with respect to x, and the partial of g with respect to v times the partial of v with respect to x. And I'm using the swirly d's because they're both multivariable functions. So partial of g with respect to u, I'm going to go ahead and leave there. Partial of u with respect to x is going to be 1 over y. Partial of g with respect to v, same thing, I'm going to leave that there. And the partial of v with respect to x is now going to be negative y over x squared. So I'm going to do the same with lowercase g sub y, which is uppercase g sub y. But again, y is in both variables, so this is dg dy times, dg du times du dy plus dg dv times dv dy. So dg du, I'm going to leave there again. Du dy is going to be negative x over y squared plus dg dv, and dv dy is 1 over x. So let's hope I did this correctly. Alright, so I want to show that x, g sub x, plus y, g sub y, is equal to 0. So x times g sub x would be dg du times 1 over y plus dg dv times negative y over x squared plus y times g sub y, so that would be dg du times negative x over y squared plus dg dv times 1 over x. So I'm going to have dg du times x over y plus dg dv times negative y over x plus dg du times negative x over y plus dg dv times y over x. These cancel, it equals 0. Yay! Alright, so now let's do an implicit. Implicit, remember, you have to make it equal to a constant, so I'm going to take this y squared and move it to the left, x cubed e to the 2y plus 3z plus 3y cubed z, I shouldn't have made it this complicated, minus 4 cosine x plus y squared equals 17. And so my partial of z with respect to y is going to be the opposite of the partial with respect to y over the partial with respect to z. So the opposite of my partial with respect to y. So let me just start from the top. X cubed 2e to the 2y plus 9y squared z plus 2y. I think that's it. All over partial with respect to z, which is going to be 3 plus 3y cubed. And that's it. Alright, I'm going to wrap it up with some application questions. Same thing, we'll take this one little bit at a time here. So let me extend this out, drag these down so I got lots of space. We'll start with our first one. The capacity C of a communication channel to carry information depends on the ratio of the signal strength S to the noise N such that this relationship is true. We have an equation for S, an equation for T, and we're going to find dc dt 1 second after the transmission has started. So again, we're dealing with chain rule because C is actually a function of S and S and N themselves are functions of T. So dc dt. Now, I think I have to correct something that I did in class. So, t is a single variable function. Like if I were to take s and n and put it into the function, I would have c in terms of a single variable. So dc dt we're going to use printed for as a result. So dc dt is going to equal, now c in terms of s is a multivariable function, so that's dc ds And then s is a single variable function in terms of t, so that's ds dt. Plus dc dn, because c itself is a multivariable function in terms of s and n, and then times dn dt. Alright, so one step at a time here. dc ds is going to be k over 1 plus s over n, and the derivative with chain rule is going to be 1 over n, and then ds dt is the derivative of cosine, which is negative sine 4 pi t, with a little bit of chain rule, 4 pi. Plus dc dn, so k over 1 plus s over n. Chain rule, so now that'll be negative Sn to the negative 2. And dn dt is going to be cosine of 2 pi t times 2 pi. Now let's see, it says after 1 second has started. So I want to figure out a couple of things. So 1 second would be when t equals 1. And then if I substitute that into s sub 1 equals 4 plus cosine of 4 pi t, which is 1. So that's 5. N sub 1 would be 2 plus sine of 2 pi, which is 0. So n is 2. So into this expression, I'm going to put in 5 for s, 2 for n, and then 1 for t as I'm going through it. So we're going to get k over 1 plus 5 halves, 1 half, sine of negative 4 pi t, oh that's 0, plus k over 1 plus 5 halves, negative 5/4, because that's n to the negative 2. Cosine of 2 pi of t is 1, and this is 2 pi. So since the first part is equal to 0, this is my dc dt. Okay, next one. Estimate this function. I'm going to name for space. So I need to define my own multivariable function here. Let's say f of xy equals e to the x cosine of y. We'll make x equal to 0, dx equals negative 0.1. We'll make y equal to 30 pi over 180, or pi over 6. And we'll make dy equal to pi over 180. So, if I were to substitute this in, f of 0 pi over 180, 30 pi over 180, would equal 1 times cosine of pi over 6, which is root 3 over 2. Now, I will need the differential, so I want to use the total differential here. So that would be dz equals the partial with respect to x, evaluated at 0 and pi over 6, times my change in x, plus my partial in the y direction, evaluated at 0 and pi over 6, times my change in the y direction. So partial with respect to x is going to be e to the x cosine y, and I will evaluate that in just a minute at 0 and pi over 6, times dx, which is negative 0.1, plus my partial in the y direction, which is e to the x negative sine y. And again, I'll evaluate that at 0 and pi over 6 in just a minute, times my change in y, which was negative pi over 180. So substituting in the 0 and the pi over 6, I'm going to get root 3 over 2 times negative 0.1 plus 1 times negative 1/2 this time, because sine of pi over 6 is negative 1/2, times negative pi over 180. Now this is my change in z. So to estimate e to the negative 0.1 cosine of 29 pi over 180, it's going to equal my z value, which I said was up here, square root of 3 over 2, plus my change in z. So the estimation would be square root of 3 over 2 minus square root of 3 over 2 times 0.1 plus pi over 360. And lastly, I figured I better do a tangent plane as well. So this one here, I have a surface, and we're going to try to find the equation for the plane tangent to the surface at the point 1, 2, 6. So the equation for a tangent plane is basically like point slope equation for a line. Z minus Z sub 0 equals my partial with respect to x at that point times x minus x sub 0 plus my partial with respect to y at that point, x sub 0, y sub 0 times y minus y sub 0. So, side work. My partial with respect to x is y squared minus 6x squared. So, evaluated at the point 1, 2, my partial would be 4 minus 6, which is, did I do that right? Y squared minus 6x squared. So that would be 4 minus 6, which is negative 2. I think. 4 minus 6, yeah. Okay, and then my partial with respect to y is equal to 2xy, and evaluated at the point 1, 2, that would be 4. So the equation of my line is z minus 6 equals negative 2x minus 1 plus 4 times y minus 2. Okay, I'm going to do a quick double check. Hopefully I didn't make any math mistakes, or not too many at least, and then I will put this on Canvas. Good luck studying this weekend, everyone.